You know how sometimes you just find yourself looking up, watching the clouds drift by, maybe seeing shapes like, I don't know, a dragon or something?
Yeah, everyone does that. It's pretty universal.
Right. But have you ever really stopped to think, what are they? Beyond just, fluffy stuff in the sky. Well, today we're doing a deep dive into exactly that. Clouds, something you see every single day, but maybe haven't fully explored.
That's right. And we've got a fantastic stack of info for you. Everything from the basic science, how they form, how we classify them, right through to cultural interpretations, and their huge role in climate. Our mission really is to unpack the most important bits, give you those aha moments, and help you get genuinely well-informed about these atmospheric wonders, without drowning you in details.
Exactly. We'll cover how they actually come into being, how scientists sort them all out, their massive impact on Earth, and even like what ancient people thought about them or what clouds look like on Mars or Jupiter. It's quite the range. Okay, let's get into it. Unpack this.
So starting with the basics. In meteorology, a cloud is essentially a visible mass. It's made of tiny liquid droplets or frozen crystals or sometimes other particles just suspended up there in the atmosphere.
Suspended in a planetary body's atmosphere, you mean?
Right, exactly. On Earth, it's usually water or ice, but elsewhere, could be other chemicals entirely.
So it's tangible, not just empty air, visible enough to see to block the sun.
Precisely. And here on Earth, they mostly form in one of two ways. The big one is when air cools down to its dew point.
Dew point. That's when it can't hold any more water vapor,
Yeah, right. It's saturated.
Exactly. And the main way it cools is through something called adiabatic cooling.
Okay, adiabatic, how does that work?
It's simpler than it sounds. Think about air rising. As it goes higher, the pressure drops.
Right.
So the air expands. And when a gas expands, it cools down.
Ah, okay. Like letting air out of a tire, it feels cold.
Kind of like that, yeah. So warm, moist air rises, expands, cools, and boom. If it cools enough to hit that dew point, you get condensation, clouds. And something usually makes the air rise, these lifting agents.
Yes, exactly. There are a few key ways air gets lifted. The most straightforward is convective lift. That's just the sun heating the ground, the warm air becomes buoyant and rises. That gives you those puffy cumulus clouds.
Okay, the classic cotton ball clouds.
Then you have frontal or cyclonic lift. This is air being forced upwards at weather fronts, where different air masses meet, or around low-pressure areas where air converges and has to go up.
So that creates different types of clouds depending on the front.
Right. Warm fronts often give you widespread, layered clouds, cirriform, stratiform. Cold fronts tend to push air up more vigorously, creating narrower bands of more dramatic clouds like cumulonimbus.
And the third one, mountains.
Or graphic lift, yeah. Wind hits a barrier like a mountain range, and the air is forced upwards. That's where you can get those cool lenticular clouds, the lens-shaped ones, or even trigger thunderstorms if the air is unstable enough.
So these invisible forces are constantly shaping the sky, and you mentioned particles.
Ah, yes. Crucial point. Condensation doesn't just happen anywhere. It typically needs a surface. In the air, these are tiny things called cloud condensation nuclei.
Like what? Dust?
Salt, exactly. Dust, salt from the ocean, pollen, even pollution particles. They're small enough to stay suspended, and they give the water vapor something to condense onto.
Right. So no dust, maybe no clouds?
It's much harder, yeah. Much higher humidity. And this lifting can go really high. Sometimes water vapor gets pushed way up past the troposphere, maybe by atmospheric wave, and forms clouds in the stratosphere or even mesosphere.
Okay, so cooling is one way to get saturation. What's the other main way?
You can also reach saturation simply by adding more moisture to the air, even if the temperature doesn't drop much.
How does that happen?
Think about evaporation from lakes, oceans, rivers, even wet ground after rain, or plants releasing water vapor that's transpiration, or sometimes rain falling from higher up evaporates on the way down, adding moisture to the air below. Virga, they call that.
And what about fog then? Is that just a low cloud?
Essentially, yes. Fog is a great example of the air reaching saturation without significant lifting. It's usually caused by non-adiabatic cooling.
Meaning
The cooling happens through contact with a cold surface, that's conductive cooling, or the ground radiating heat away at night, radiational cooling, or even evaporative cooling. This happens right near the ground, so you get condensation at surface level. That's fog. Or mist, if visibility is a bit better.
Got it. Now, you mentioned classification earlier. How do scientists make sense of all the different cloud shapes and types we see? It seems like there's an endless variety.
There's a lot of variety,
Yeah.
but there's a really elegant system, actually. It's hierarchical.
Yeah.
Think of it like a family tree for clouds in the troposphere. That's our weather layer, closest to the ground.
A cloud family tree. I like that.
It starts with 5 basic physical forms that a cloud generally takes. Then you combine those forms with the altitude level, where they typically occur high, middle, or low. And that gives you 10 basic genera. Those are the main types, like cirrus or cumulus.
Okay, so 5 forms first. What are they?
All right, thinking about them generally from most stable air to least stable. First, you have stratiform. These are the flat, featureless, sheet-like clouds. Think overcast gray days. They form in very stable air.
Okay, sheet-like. Got it.
Then cirriform. These are the delicate, wispy ones, usually found very high up, made of ice crystals. Think thin, feathery streaks.
Like cirrus clouds.
Exactly. Third is stratocumuliform. This is sort of a mix, layers or patches that show some lumpiness, rolls, or ripples. It means there's some limited convection, some instability.
So not quite flat, not quite puffy.
Right. The cumuliform. These are your detached heap-like clouds, the cotton balls. They result from localized convection, rising thermals.
Fair weather clouds, usually.
Often, yes.
Mm-hmm.
And finally, cumulonimbus. These are the big ones. Towering, massive vertical development, often have that anvil shape at the top, form in very unstable air. These are the thunderstorm clouds.
Okay, those 5 forms make sense visually. So how do they combine with altitude to give us the 10 main genera?
Right, let's break that down by level, starting high up. High-level clouds, these are way up there, 3,000 to maybe over 18,000 meters, depending on latitude. All ice crystals. You've got cirrus, those wispy streaks we mentioned.
Okay.
Cirrocumulus, CC, like a very high layer of tiny white ripples or grains, sometimes called a mackerel sky, can produce virga, that evaporating rain.
Mackerel sky, right.
And cirrostratus, CC cirrocranus, a thin, sort of whitish veil that often covers the whole sky and creates those halos around the sun or moon. Doesn't rain, but often means rain is coming.
Okay, high ice clouds. What about the middle level?
Mid-level clouds, found roughly between 2,000 and 7,600 meters. Often a mix of water droplets and ice crystals, especially at the colder end. 2 main types here, altocumulus and CC. These are patches or sheets, often grayish or whitish with waves or rounded masses. Bigger elements than cirrocumulus and some shading can also produce virga.
Like a slightly lower, lumpier version of cirrocumulus?
Kind of, yeah. And altostratus, A's. This is the grayish or bluish sheet, more uniform than altocumulus. Sometimes the sun looks like it's shining through ground glass. This one can produce light, steady rain or snow.
Okay, the watery sun cloud.
And then low-level.
Low-level clouds. Bases below 2,000 meters. Mostly water droplets, unless it's very cold, appear larger. We have stratocumulus, SC. These look like low, lumpy layers or patches, often with darker gray bases, bigger elements than altocumulus. Might produce very light drizzle.
So lumpier than stratus.
Right. Then stratus itself. This is the gray, featureless low layer, like fog that hasn't reached the ground. If it produces anything, it's just drizzle or maybe light snow grains.
And cumulus, you mentioned that earlier.
Yes, cumulus clouds usually have their bases in the low level. We're talking about the standard fair weather cumulus, small with flat bases. They don't usually precipitate.
Okay. That covers high, mid, and low. But some clouds seem to span multiple levels. Exactly. We categorize those based on their vertical development. There are 2 main groups here. First, moderate vertical development. The key one here is nimbus gratus, NS. This is your classic rain cloud, a thick, dark gray, often widespread layer. It typically forms from thickening altostratus. Its base lowers into the low level, but the top can reach high levels, produces steady rain or snow, often associated with warm fronts.
So nimbus gratus is officially mid-level, but acts multi-level.
The WMO classifies its base usually in the mid-level, yes, but functionally it occupies a large vertical slice. Also, slightly larger cumulus clouds, cumulus mediocris, have moderate vertical extent, but are still officially low-level clouds.
Okay, and the really big ones.
The towering vertical clouds. These are the ones pilots really watch out for. Bases in the low to mid-level, tops reaching way up high. There's cumulus congestus. These are like cumulus clouds on steroids. Much taller than they are wide cauliflower-like tops. They can produce showers, sometimes called towering cumulus or TCU.
Getting bigger.
And the biggest of all, cumulonimbus, CB. Immense, heavy, towering masses. Dark bases, tops often spreading out into that anvil shape made of ice. These are the thunderstorm factories. Heavy downpours, lightning, hail, strong winds, tornadoes. The works.
Wow, that's a comprehensive list. You mentioned even more detail. Species and varieties. Like, give me an example that really stands out.
Oh, definitely. The system gets finer. Species, describe specific structures, often related to stability or wind shear. One really striking species is lenticularis.
Lenticular clouds, yes. Those smooth, lens-shaped ones.
Exactly. Often seen near mountains. They form in stable air flowing over terrain, creating standing waves. They look serene, but they can indicate really strong turbulence for aircraft. Sometimes they stack up like pancakes. Very distinctive.
They are amazing. Okay, so that's a species. What about other unique features or varieties?
Varieties describe patterns or opacity, like if a cloud layer is see-through, translucidus, or opaque, opacus, or arranged in waves, undulatus, or rows, radiatus. But then you have supplementary features, things attached to the main cloud. And this is where you get some spectacular sights. One of my favorites is mammatus.
Mammatus, those pouch-like things hanging underneath.
Precisely. Bubble-like protuberances, usually seen on the underside of a cumulonimbus anvil after a storm has passed its peak. They look dramatic, almost otherworldly. Don't necessarily mean severe weather is happening right then, but they're associated with strong storms.
They look incredible. What about clouds that look like breaking waves?
You're probably thinking of Fluctus or Kelvin-Helmholtz wave clouds. They're quite rare. They form when two layers of air are moving at different speeds, creating this beautiful shearing instability that looks exactly like ocean waves curling over. Really stunning.
And there's a newer one too, Asperitas.
Yes,
Yeah.
Asperitas. Recognized more recently, these look like the underside of a very rough sea. Chaotic, dark, undulating waves. Quite dramatic and a bit ominous looking.
And then there are clouds actually made by things on Earth, like fires or planes.
Absolutely. We have categories for those. Flammagenitus clouds born from intense heat, huge wildfires, volcanic eruptions. Some volcanic ones have reached incredible heights, like 57 kilometers.
Whoa!
And homogenitus clouds are human-made. The most common example, contrails from airplanes. If they persist and spread, they're classified as cirrus homogenitus. They can actually affect local temperature and sunshine.
Fascinating. So we've covered the troposphere pretty thoroughly, but you said clouds exist higher up and even on other planets.
We did, yeah, way beyond our everyday weather layer. And even looking down from high up, you can see amazing large-scale patterns, like vast stratocumulus fields over oceans, sometimes organized into these cells, cloudy centers with clear edges, or clear centers with cloudy edges. Open and closed cells.
Like a giant honeycomb pattern.
Sort of, yeah. And another cool pattern is vortex streets. These are swirls, eddies, formed downwind of obstacles like tall islands. Clouds like altocumulus get caught in these wind patterns called Kármán vortices, creating these amazing parallel rows that twist and turn. You see them in satellite photos sometimes.
Very cool. Okay, so let's go higher. Beyond the troposphere.
Right, up into the stratosphere, we find polar stratospheric clouds, or PSCs. These are typically way up 15 to 25 kilometers. Very cold, very little moisture up there, so they're mostly restricted to the polar regions in winter.
And they look different.
Yeah, they're not classified with the Latin system. There are two main types. Type 1 clouds are made of supercooled nitric acid and water. They look hazy, maybe like cirrostratus. Importantly, they play a role in ozone depletion.
Oh, okay.
And type 2 are the really beautiful ones called nacreous clouds or mother-of-pearl clouds. They're made of water ice crystals, very thin, and they shimmer with these incredible iridescent colors, often look wavy or lens-shaped, like high-altitude cirrus or lenticular clouds.
Mother of pearl sounds amazing, and even higher than that.
Even higher. Right near the top of the mesosphere, around 80 to 85 kilometers up. That's about 10 times higher than cirrus clouds. These are mesospheric clouds, or more commonly, noctilucent clouds.
Noctilucent. Night shining.
Exactly, because you only see them when the sun is well below the horizon for you on the ground, but it's still illuminating them way up high. They look like brilliant electric blue or silvery white wisps, almost like eerie cirrus clouds.
Wow, where do you see those?
Also mostly restricted to polar regions, mainly in summer. Interestingly, they seem to be becoming more frequent and brighter, which might be linked to climate change, possibly due to increased methane releasing water vapor way up high when it breaks down.
Okay.
They form on tiny particles, possibly from meteor smoke.
Meteor smoke. Okay, that's wild. And then beyond Earth, what are clouds like out there?
Oh, the variety is incredible. Venus is completely shrouded in thick clouds, but they're not water. They're sulfuric acid, multiple layers of stratiform clouds.
Sulfuric acid rain. Lovely.
Well, it probably evaporates before reaching the surface virga again. Mars has water ice clouds, thin ones, kind of like cirrus or cirrocumulus, mostly near the poles, and also ground fogs made of water ice.
So Mars has weather, sort of.
It does. And the gas giants. Jupiter and Saturn have spectacular cloud decks. An outer layer of ammonia ice clouds, looking cirriform. Below that, a layer of ammonium hydrosulfide clouds. And deeper still, clouds of water ice and liquid water, possibly including huge cumulonimbus thunderstorm clouds, especially near Jupiter's Great Red Spot.
Multiple layers of different chemicals.
Exactly. And Uranus and Neptune, the ice giants, their visible clouds are primarily methane ice. Saturn's moon Titan is fascinating, too. It has methane clouds, including cirrus and polar stratospheric types, as part of a whole methane cycle, like Earth's water cycle, but with methane rivers and lakes.
A methane cycle, wow, and even beyond our solar system.
Yeah, astronomers are detecting clouds on exoplanets. They found evidence of high-altitude, thick clouds on planets like Kepler-7b and GJ-1214b. It tells us clouds are probably a common feature of planetary atmospheres throughout the universe.
Okay, this is all fascinating stuff, but it brings up a big question. Why should you, listening right now, care so much about cloud details? It turns out they're not just pretty patterns, they have a huge impact.
A massive impact.
Yeah.
I mean, first, obviously, they're where precipitation comes from rain, snow, hail. Life depends on that.
Yeah.
But they also drive atmospheric circulation by releasing heat when water condenses, and they redistribute heat around the planet. And then there's their effect on climate, which is complicated. Clouds have a dual role.
Cooling and warming, right.
They have a cooling effect. Cloud tops, especially low and mid-level ones, are bright white. They reflect a lot of incoming sunlight back into space. This increases Earth's albedo, its reflectivity, and that cools the planet.
Okay, like a giant sunshade.
Pretty much. But then there's the warming effect. Clouds, being made of water and ice, are also very good at absorbing the heat radiation coming up from the Earth's surface, that infrared radiation. They then radiate some of that heat back down, trapping it like a blanket. This is similar to the greenhouse effect.
And different clouds do this differently.
Yes. High, thin ice clouds like cirrus are better at trapping heat than reflecting sunlight, so they tend to have a net warming effect. Low, thick clouds like stratocumulus are much better reflectors, so they have a strong cooling effect.
So what's the overall balance, cooling or warming?
Right now, based on measurements, NASA says the global cooling effect from clouds is larger than their warming effect. So overall, clouds currently cool the planet compared to if they weren't there.
Okay, that's significant. But what about the future, climate change?
That's the billion-dollar question, or maybe trillion-dollar. How clouds will respond to a warmer world and how those changes will further affect warming these cloud feedbacks are incredibly uncertain.
How so?
Well, warmer air can hold more moisture, which might mean more clouds, potentially increasing cooling. But warmer temperatures might also cause some clouds to evaporate, reducing the cooling effect. And the types of clouds might change, shifting the balance between warming and cooling.
So we don't really know which way it will go.
It's the single biggest source of uncertainty in climate models. Different models predict different cloud responses, leading to different projections of future warming. Understanding cloud feedbacks is absolutely critical for predicting future climate change accurately. It's a huge area of research.
Oh, okay. So clouds are crucial for climate, but let's not forget they're also just beautiful. The colors, the light.
Oh, absolutely. Their appearance tells us so much. Their brightness depends on how much light they reflect, scatter, and absorb. Thick clouds reflect most sunlight hitting them, hence the brilliant white tops. The bases look darker simply because less light gets through.
And the colors at sunrise and sunset.
That's all about the light scattering. Sunlight has to pass through more atmosphere at dawn and dusk, scattering away the blues and greens, leaving the reds, oranges, and pinks to illuminate the clouds. Beautiful effect.
What about weird colors, like green clouds?
Yeah, greenish or sometimes bluish tint in a really big cumulonimbus cloud usually means there's a lot of water and potentially hail within it. The ice and water scatter light in a particular way. It's often seen with severe thunderstorms, indicating a very deep, wet storm with a strong updraft, but it's not like a direct predictor of a tornado or anything on its own.
Still a sign to take cover.
Definitely a sign of a potent storm. You might also see yellowish clouds sometimes, usually due to pollution smoke from wildfires or nitrogen dioxide in cities.
And finally, beyond science and weather, humans have always had a relationship with clouds, haven't they? In culture, religion.
Absolutely, for millennia. You find clouds woven into mythology and belief systems everywhere. The ancient Akkadians saw clouds as the breasts of the sky goddess Antu. Rain was her milk.
Yeah.
In the Bible, you have Yahweh guiding the Israelites as a pillar of cloud and Jesus ascending into a cloud. In some traditions, clouds are celestial realms or beings, even in philosophy and literature. Aristophanes, the ancient Greek playwright, wrote a comedy called The Clouds, where they are portrayed as the only true deities, shifting shape, sources of inspiration.
So powerful
Very
symbols.
powerful. In China, clouds are traditional symbols of luck and happiness. Different patterns and colors represent multiplied blessings or eternal joy. And even today, think about just cloud watching, looking for shapes. That's a simple modern connection to that ancient sense of wonder, a form of pareidolia, seeing patterns and randomness.
It really is a universal thing. Wow, what a journey from, the basic physics of water droplets and ice crystals through that incredibly detailed classification system, their huge role in climate, both cooling and warming, and that big uncertainty, and right into mythology and art. You really do have a much deeper appreciation for clouds after all this. There's so much more than just background scenery.
Exactly. It shows how even the most familiar things we see every day, hold these incredible layers of complexity and meaning. Science, history, culture, it's all up there.
So
Yeah,
think
I mean,
about it. What really stood out to you from our deep dive today? Next time you look up, are you just going to see a cloud? Or are you going to see, I don't know, a cumulonimbus capillatus and Mauritius? Or maybe think about its albedo effect. Or just see a dragon.
and maybe something to mull over.
Yeah.
These clouds aren't static. They are a dynamic reflection of our atmosphere right now, but they're also profoundly shaping its future. And as we've discussed, they hold one of the biggest uncertainties in understanding climate change. What insights, what warnings or reassurances might we gain if we just paid a little closer attention to the ever-changing story they're telling above our heads?